8.3, growth functions. In this part, we will learn this new concept, growth functions. Yeah. All right. First, let's look at the running time formula. When we study the running time formula, there is some interesting pieces we need to consider. Yeah. All right. First, notations. To represent the running time, we use T function, capital T of n, for the problem size n. Yeah. Then, another useful quantity we need to represent. So that is the function of the number of basic operations, C of n. Counting number, C of n, problem size n. Yeah. Then another constant we need in our representation, execution time of one basic operation. One basic operation, it takes certain amount of time. We treat that as a constant. So C op, yeah. Little c sub op. Yeah. Then we can write the relationship, the formula between running time and the counting number, C of n. Yeah. Very simple. Yeah. We use approximation representation. May not be very precise, yeah, but pretty close approximation. So that is T of n approximately equal C op multiply C of n. Yeah, so that's pretty straightforward, right? One basic operation, you need C op, that much time. But now you have capital C of n basic operations. So that's why you just do the multiplication directly. But why we still use that approximately equal that symbol, yeah, that notation? It's pretty obvious because there are also some non-basic operations, right? Here, we do not factor in the non-basic operations. Okay, yeah. So we need to spend some time on non-basic operation. So we skip that part. Yeah. So for that reason, we can only say this is an approximation expression. So not precise expression, but that's good enough. Yeah. All right. Here, based on this expression, we can treat T of n and C of n, the relationship between these two functions, proportional, right? Proportional, yeah, because of this constant multiple factor. So proportional, yeah. If they are proportional, then when we measure one, that's indirectly measure the other one, right? Proportional, okay? This one bigger, that one also bigger. So this one smaller, that one also smaller. Proportional, right? So in that way, we can switch our study focus from T of n to C of n, because the counting number C of n much easier to calculate. Execution time much harder to calculate. Yeah. So if we work on C of n, much easier. Without doing any experiment, we can get a pretty good idea to describe how fast is the algorithm. That's what we need to do. Yeah. All right. Yeah. Next, approximation approach. So we want to look at some more other details for this approximation approach. All right. When we apply approximation approach, we should do it in the right way. So what is the right way? Yeah. So here, from this observation, all right, we have this simple observation. Efficiency of algorithm is reflected when the input size is large. Okay, input size is large, reflected, not small. Yeah. So for small inputs, it's hard to distinguish efficient algorithms from inefficient ones. Yeah. So let me explain this part. Why, when we do approximation analysis, when the input size is large, we get very good approximation or estimation. Yeah. When the input size relatively small, our estimation will not be very good. Will not be very good. So when the problem size relatively small, the slower algorithms could do better than the faster algorithms. Why? The reason is very simple. Overhead factor. You need to consider that. What's the overhead? When you implement an algorithm, do you need to do preparation? You need to do a lot of work to do preparation. Okay? So set up here and there, do a lot of things. Overhead part takes some time, right? Yeah. How important is the overhead part? How important is the overhead part? It depends on your problem size. When the problem size is relatively small, then the overhead part comparatively pretty big. Yeah, comparatively pretty big. But when your problem size becomes larger and larger, you pretty much use the same overhead time, same. But you need more and more time to work on the basic operations, more and more basic operations. So the proportion of that overhead part will be smaller and smaller. Finally, too small, we can ignore it. But when the problem size is relatively small, you cannot ignore. The overhead part, probably 40–50% of your total execution time. How can you ignore it? You cannot. But when your problem size very big, the overhead part usually less than 1%. Usually less than 1%. Can you ignore it? Yes, less than 1%. So we can comfortably ignore it. So that's the first commonly used guideline here. Yeah. All right, another one. Conclusion. Yeah. So when we do analysis on algorithms, we should focus on large input, not small input. Yeah. So based on the observation, so we have this kind of conclusion. So we don't worry about the small inputs because we get a lot of distortion from overhead part. So we want to compress that distortion part, overhead part. How do we compress? When we look at the problem in large input sizes, we compress the overhead part, the distortion part. Yeah. All right. So then, in order to study the efficiency measure when the problem size is very large, we need some nice notations. Notation here, very important. We need nice notations. The notations should be simple, but good enough to describe what we need. So that kind of notation. Yeah. All right. Yeah. So let's look at the next part. Yeah. Ignore unnecessary details. Yeah. All right. We start from this approximation formula. Yeah. Yeah. So we recall it a bit. T of n running time function. Yeah. C of n number of basic operations. C of the cost of a basic operation. Here, when we say cost, we mean execution time. We spend this much time, that's our cost. Yeah. All right. In order to make our study, our analysis as simple as possible, we take this approach. Remove unnecessary details to reveal the most important factor. We may have a lot of details. Some details not very important. So we can ignore those details. Yeah. What kind of details we can ignore? Yeah. So here, yeah. Some constant we can ignore. Constant. Some constants we can ignore, but some we cannot. Okay? Yeah. So we need to look at what kind of constant they are. Yeah. All right. Another, we can ignore some minor terms. Other than constant, you have major terms, minor terms. But some minor terms we can ignore. Yeah. All right. So let's understand these things. Yeah. All right. First, let's look at this ratio. Left-hand side, the ratio of two running time functions when the problem size doubled, 2n over n, double, problem size doubled. Okay, yeah. Right-hand side, counting number of basic operations, two functions, the ratio when the problem size is doubled. Yeah. They approximate equal because you can see the C of the constant part cancel out. Cancel. Okay? Yeah. All right. And this ratio can reflect how fast it changes when the size doubled. Yeah. Because we want to look at the function change. Right? Every time when we double the problem size, then how many times we can increase our execution time function or number of basic operation function. Yeah. So we want to look at that. Yeah. But when we look at that ratio, so you can see the C up, that constant, not important in this ratio, right? Yeah. So that means that kind of constant can be ignored. Okay? Without knowing that constant, we can still see how fast that function grows, right? Yeah, we can see that. Yeah. Yeah. All right. Next, we want to understand this minor terms, this part. Yeah. All right. Because we want to keep the major terms and ignore the minor terms. But what do you mean major terms, minor terms? Yeah. Here, let me use simple example. We can see that easily. Yeah. use growth function to measure efficiency. Here we introduce a new concept called a growth function. So what do you mean? What is the growth function? In the example we did before, we can see that growth function. All right, so what is the major term? They are related, right? So major term, dominant term. We learned the concept dominant term before, right? When we do the sequential search, linear search. Remember, I described one term that is the dominant term. Later we will see the dominant term more, many times later. Here, the major term. Okay. In the selection sort, let's look at what is the dominant term, what is the major term, the minor term. We can see that. In this array, when we do the selection sort, we get the counting number for the number of basic operations in this formula. If we expand this formula, we have two terms. The first one, 1/2 n squared. The second term, minus 1/2 n. Two terms. Here you can see the first one major term, the second one minor term. Okay? And the first one we can also call dominant term. Why dominant? The first one dominates the second one. How do you see the first one dominates the second one? We use limit. We can see the dominance using the limit calculation. For the question, I ask you to think about it. Best case, worst case, average. Here, I give you the answer. For these three cases, the answer is the same. The answer are the same. The best case, worst case, average case, or take this number. The same. You have no other choice, only this one. All right. Then let's look at the dominance part. So view the dominant term through the limit calculation, simple limit calculation. The first term over the second term. We don't need to take that negative sign. That's not important. We just look at the absolute values. I hope you know the limit concept. In calculus, you have that background, limit, how to calculate basic limits. Here, this limit is very easy to calculate. First, we cancel out 1/2, 1/2. That's same constant, right? Also, we can cancel out 1n. That n cancellation, so limit of n when n goes to infinity. That is still infinity. So you can see the ratio of two terms goes to infinity. Can we say the top term dominates the bottom term? Yes. Infinity, that's dominant. Dominance. Infinity tells us the dominance. Okay? Yeah. All right. So from there, you can understand why we call the first term the dominant term. Next, our growth function concept. What is the growth function? First, from the dominant term, look at this dominant term. You take away the constant. The constant we know, here, in this part, the constant not important. So when we consider growth function, we do not want to include that constant, the leading constant in front of the dominant term. We skip it. So we get an n squared. That n squared we call the growth function of that c function, c of n. That's that function, c of n, the growth function. we do not include the leading constant of that function. Yeah. All right. So that's the, introduction of the concept, the growth function. Yeah. So we finish part C, yeah, because we do not have enough time to do exercise questions. So later we will leave exercise part, in other parts we will spend more time on exercise questions. Yeah. All right, so let me